This video is going to introduce the idea of mixed strategies and explain why they're important to Nash equilibrium. So the example that I want to think about here is the United Nations setting up checkpoints to defend against terrorist attacks at a port in Somalia. And you can see that what happens is they place a checkpoint on the road, they stop all cars, like this taxi here, and they go through the contents of the car to make sure that it doesn't contain any explosives or other dangerous materials. Now, let's think about this situation as a game. So there are a variety of different roads that the UN could choose to set up its checkpoint on every hour. And for each one of those roads, the potential attacker could decide to attack that road. And if it's the case that the defender defended that road and the attacker attacks it, then the attacker gets a large negative payoff because they're captured and their attack is not successful. If, on the other hand, the attacker attacks any other road, then the attack is successful, and then the utility of the attacker depends on the value of the target that was attacked and wasn't defended. Now, it's pretty clear that if the UN were to commit to any deterministic strategy, if they were to choose their action in any deterministic way, things are going to go pretty badly for them, because the attacker would be able to look at what they're doing, they'd be able to watch for a while, see what strategy the UN is following, and then attack something different, and attacks would always be successful. So it must be that this is not really how checkpoints get set up. And indeed, what really happens is that the checkpoints are set up in a randomized way, so that even if the attackers watch for a while and figure out what the randomized strategy is, they're not able to know on a given hour where the checkpoints are going to be. And this means that the value of an attack is limited. So the Nash equilibrium of a game like this is going to involve the defender defending in a randomized way like this. And this kind of a randomized strategy is called a mixed strategy. And that's going to be the topic of the next sequence of videos. This lecture is going to introduce the idea of mixed strategies and extend our previous concept of Nash equilibrium to this new definition. Let's begin by looking at the matching pennies game. Recall that it would be a pretty bad idea to play any deterministic strategy in this game. For example, if player 2 were to play heads, then player 1 would want to respond by playing heads to get a payoff of 1, meaning that player 2 would prefer to change to tails so that he can get this payoff of 1, meaning that player 1 would prefer to change to tails so he can get this payoff of 1, meaning that player 2 would prefer to change back to heads to get this payoff of 1, meaning that player 1 would prefer to change back to heads as well to get this payoff of 1 where we started. And so you can see there's kind of a cycle where we just bounced around between the different cells of this game matrix and essentially argued that no pair of deterministic strategies works for both players. So what does work for both players? Well, essentially it does make sense for players to confuse each other by choosing to play randomly. So intuitively, instead of saying, I'm going to commit to playing heads or I'm going to commit to playing tails, I can say, I'm going to commit to flipping this coin and playing whatever side comes up. So let's try to make this idea formal. Before we talked about the idea of pure strategies, which we just equated to playing actions. Now let's think of things in terms of probability distributions. So let's say that a strategy for an agent is any probability distribution over the actions that the player has available to him. And a pure strategy then is the special case where I play only one action with positive probability. A mixed strategy says I'm just going to play more than one action with positive probability. There might be a couple of different actions that I assign positive probability to, like in my example with matching pennies. I'm going to call the support of my mixed strategy the set of actions that get positive probability. So for example, when I flip a coin when I'm playing matching pennies, both heads and tails are in the support of my mixed strategy. My support is the set heads, tails. I'm going to define the set of all strategies for an agent I to be capital S sub I. And I'm going to define the set of all strategy profiles, capital S, to be the Cartesian product of these strategy sets for the different agents. Now I have the problem that I've elaborated my definition of strategies in the game to include not just this finite set of things players can do, but this infinite set of all of the probability distributions over these finite sets. The reason this is a problem is I only have a utility definition for action profiles. And now I'm allowing things to happen that I don't have utilities for. That is to say, I can't just read a number out of the game matrix to figure out how happy the players are when something happens, because under a mixed strategy with a support of size greater than 1, I won't always end up in the same cell of the matrix. So I can extend my definition of utility here by leveraging the idea of expected utility from decision theory. So these equations explain what this means. It looks a lot more complicated than it is. So what I'm saying here is that I's utility under mixed strategy profile S, where little s is some element of the set of all possible mixed strategy profiles, big S, is equal to the sum over all action profiles in the game. You can kind of think of this intuitively as the sum over all of the cells in the normal form of the game, where I take the utility of each cell and I multiply it by the probability that that cell will be reached in the given mixed strategy. The probability of getting to cell A, strategy profile A, action profile A, given strategy profile S. And then, of course, I need to define what this probability actually is, and that's given here. The probability that I'll get to a given action profile given a strategy profile S is just the product of the probability of each player playing his part of that action profile. So, for example, if this player was playing with probability 0.5 on each action, and this player was playing with probability 0.5, then the probability that I would get to this cell is 0.25. This action profile arises with probability 0.25 because this thing happens half the time and this thing happens half the time, and so we have to multiply those two probabilities together to get the joint probability of this action profile. So that's what this definition here is saying. So in total, my utility for a strategy profile is my expected utility, taking an expectation over all of the action profiles in the support of that strategy profile and weighting each of them by the probability that that action profile would actually arise. Well, now that I've defined what strategies are, I can go back to my definitions of best response and Nash equilibrium. And basically, they work the way they did before, except I change all of the A's to S's. So that means I have to write these definitions again, and I'll go through them again. But conceptually, if you understood what best response and Nash equilibrium meant in the case of actions, then everything will work again. So I will say that a strategy S star I is an element of the set of best responses to strategy profile S minus I when the following condition is true. For all other strategies Si that player I could take, for all of the strategies in the set of possible strategies for that player, and notice that this is an infinite set, but that's okay, the definition still works, then the utility that the player would get for playing S star I when everybody else plays the strategy profile S minus I is at least as big as when he plays this other strategy Si. So let me say that again. S star I is a best response to strategy profile S minus I if it's at least as good as anything else, given that everybody else is playing S minus I. Now we can say that a strategy profile S is a Nash equilibrium if it's the case that for all agents, everybody is playing a best response. Incidentally, you might notice that I'm using a set membership operator here rather than an equal sign, which is what you might have expected to see. Well, the reason I don't use an equal sign is because the set of best responses might have more than one thing in it. So there might not be only one best response. Sometimes there'll be multiple best responses. And so here what I'm saying is a strategy profile is one of the best responses if this condition is true. And I'm saying a strategy profile is a Nash equilibrium if everybody is playing one of their best responses. Well, this might seem like much ado about nothing. I've introduced this idea of randomizing as a strategy. I've redefined utility. Then I've leveraged this redefined definition of utility, which is incidentally what I'm using here when I talk about the utility of a strategy profile, to define best response. I've then leveraged that definition of best response here to talk about Nash equilibrium. And in total, I've just ended up kind of saying everything that you've already heard us say. But what does matter is that now that we have a new definition of Nash equilibrium, we're able to state a theorem that we didn't have before. And this is Nash's famous theorem. This is the reason why Nash gets the Nash equilibrium named after him. And this is one of the main reasons why Nash got the Nobel Prize. This theorem actually didn't take very long to prove, but it's a really important thing for game theory. And the theorem is that every finite game has a Nash equilibrium. First of all, what is a finite game? This sounds like I'm hedging here, but it's not much of a hedge. A finite game just means that the game takes a finite amount of space to write down. So it has a finite number of players. It has a finite number of actions for every player. And that means it has a finite number of utility values in the game, because the number of utility values is determined by the number of players and the number of actions for each player. So as long as the game has a finite number of players, not just 2 players, but any finite number of players, and a finite number of actions for each player, not just 2 actions, but maybe a very big game, then no matter what the payoff values are, no matter what strategic situation we're talking about here, no matter what real-world interaction this is modeling, there's going to be at least one Nash equilibrium in this game. That's a pretty deep thing. That's saying there will always be some stable thing that all of the players can do, which has the property that if they knew what everyone was doing, none of them would want to change their strategy. That's basically one of the main reasons why we care about this idea of Nash equilibrium, because we know that no matter what the game is, we can find such a Nash equilibrium and reason about it. That's why Nash equilibrium is such a powerful thing. And that's only true when we have this fuller definition of Nash equilibrium here that we've just defined in terms of strategies. We saw that when we talked about Nash equilibrium in terms of just actions before, what we'll now, from this point on, refer to as pure strategy Nash equilibrium. So pure strategy Nash is when we do all of this with A's instead of S's. That's a pure strategy Nash equilibrium. And the sad thing about that is that we don't get a theorem that says that every finite game has one of those. But this mixed strategy Nash equilibrium always exists. Let's do some examples. So remember matching pennies? Well, we just argued at the beginning of this video, effectively, that matching pennies doesn't have a pure strategy Nash equilibrium. But it does have a mixed strategy Nash equilibrium. It has one. And that is, as I suggested before, for both players to randomize 50-50. And that doesn't mean that it always has to be 50-50. That just happens to be what the Nash equilibrium is here. That comes from the symmetry of the payoffs. But that turns out to be the Nash equilibrium here. let's come back to the coordination game. Well, we've previously seen that these two strategy profiles, I'm circling outcomes, but remember an outcome isn't an equilibrium. 1-1 isn't the equilibrium. That would be wrong to say. The right thing to say is that left is an equilibrium. Right is an equilibrium. But it turns out there's another equilibrium here. So it turns out, again, 0.5 is a Nash equilibrium here as well. And that's kind of funny because it doesn't seem like 0.5 is such a good thing to play in this game. But you can confirm to yourself that if player 1 is randomizing by playing 50-50, then player 2 can do no better than to randomize 50-50. Now you'll notice that player 2 could do just as well by playing something else. If player 1 is playing 50-50, player 1 is just as happy to go left all the time. But in particular, if player 1's going 50-50, player 2 can do no better than to go 50-50 himself. The reverse is also true, and that makes 50-50, 50-50 a Nash equilibrium of the coordination game as well. And let's look at prisoner's dilemma. In prisoner's dilemma, we've previously seen that this is an equilibrium, and it's an equilibrium in strictly dominant strategies. And we argued before that equilibria in strictly dominant strategies are unique. And so what that means is, indeed, there aren't any mixed Nash equilibria of the prisoner's dilemma. This is, in fact, the only Nash equilibrium. In this video, we're going to look at how to compute the mixed Nash equilibria of a normal form game. And in particular, we're going to go through the example of battle of the sexes. So what you've seen so far about equilibria kind of suggests that it's really easy to come up with an equilibrium. But in fact, as games get big and general, sometimes it can be pretty tricky to find the equilibria of a game. And Nash's theorem is kind of a funny theorem because it tells us that something exists, but it doesn't tell us how to find it. It just tells us that it has to be there. It's a non-constructive argument. So what I'm going to tell you today is sort of a starting point to finding an equilibrium, which is enough that it works in small games. In fact, you can turn this into a general algorithm, but not necessarily the most efficient or insightful way of finding equilibria. So what I want to tell you today is that it's easy to compute a Nash equilibrium if you can guess what the support of the equilibrium is. So recall what a support is. A support is the set of pure strategies that receive positive probability under the mixed strategy of the players. So an equilibrium support is a set of actions that occur with positive probability. For example, that might be the support of an equilibrium. So for battle of the sexes, let's guess that the support of the equilibrium is all of the actions. So let's look, and intuitively, that if there's going to be a mixed strategy equilibrium of this game, that looks like what it should be. So let's guess that that's the support, and then try to reason about what the equilibrium would have to be given that support. So let's just introduce some notation to make this work. Let's let player 2 play B with probability P, and F with probability 1 minus P. Now, if player 1 is going to best respond to this mixed strategy, whatever it is, and be playing a mixed strategy in response, then we can reason that player 2 must have set P and 1 minus P in a way that makes player 1 indifferent between his own actions, B and F. So this is an important point in reasoning about how mixed strategies work. So I encourage you to stop the video at this point and just think about why that would be true before I tell you the answer. So the reason why player 1 needs to be I don't have the answer on the slide, I'll just tell you. The reason why player 1 needs to be indifferent is that he's playing himself a mixed strategy, which means some of the time he's playing B and some of the time he's playing F, right? Because these are both in the support, they both get played with non-zero probability. And if this is an equilibrium, then this is a best response that player 1 is playing. Well, if player 1 can play B some of the time and F some of the time and be playing a best response, he must be indifferent between playing B and F. If he's not indifferent, if, let's say, B is better, then he could get even more utility by reducing the amount of probability he puts on F and increasing the amount of probability he puts on B. And in fact, he could get the most utility by putting absolutely no utility on F and just all of the utility on B. So the only way that he would actually want to play a mixed strategy is if it's just the same for him to play B and F. So that means that we can reason that player 2 has set his probabilities P and 1 minus P in such a way that makes player 1 indifferent. And the reason why we've bothered to think about this is we can actually write that down in math. So we can say the utility for player 1 of playing B, and here I'm kind of abusing notation. You should really understand this to mean the utility for player 1 of playing B, given that player 1 plays P 1 minus P, is equal to the utility of player 1 for playing F, again, given that player 2 plays P 1 minus P. So then we can simply expand this out, taking into account the actual payoffs of the game, and learn something useful. So we can say, if it's the case, given the same probabilities, P and 1 minus P, that player 1 is indifferent between playing B and playing F, then that means, well, when he plays B, then he gets 2 with probability P, and he gets 0 with probability 1 minus P. So that's what we have written down here. And when he plays F, he gets 0 with probability P and 1 with probability 1 minus P. And that's what we have written down here. And now we just have a simple equation in one variable. So if we rearrange it, we end up concluding that the only way that player 1 can be indifferent between playing B and F is if P is equal to 1/3. In the same way, we can reason that if player 2 was randomizing, which we had just assumed that he was, then player 1 must make him indifferent. And why is player 1 willing to randomize? Because he's simultaneously being made indifferent by player 2. So now let's say that player 1 plays B with probability Q and plays F with probability 1 minus Q. So now we can just do the same thing as before, where again, you should understand this to mean Q 1 minus Q, and likewise here. And we can just expand it out in the same way. So if player 2 plays B, then he gets 1 with probability Q, and he gets 0 with probability 1 minus Q. And if he plays F, he gets 0 with probability Q, and 2 with probability 1 minus Q. We now again have an equation in one variable, and we can rearrange it and find that Q is equal to 1/3. And the important thing to notice that happened here is that player 1 and player 2 were both willing to randomize. So we ended up getting out numbers here that made sense. We ended up getting P's and Q's that were probabilities. They were between 0 and 1. And that means it's actually possible to set them in such a way that player 1 and player 2 actually would be indifferent. If the payoffs were different, we might have gotten something out here like 13. And if Q is 13, it means that B would have to happen 13 times more often than F for player 1 to be indifferent. And because that's not a probability, what that would really be telling us is there's no way of making the other player indifferent. And that would tell us there can't be an equilibrium with this support. But what we got out was interpretable as a probability, and that means there is an equilibrium with this support, because what we've seen is if player 1 plays this way and player 2 plays this way, then they each make each other indifferent. And if they both make each other indifferent, then they're both willing to play these mixed strategies. And so in the end, this mixed strategy profile is a Nash equilibrium. And so what we've done then is to compute a Nash equilibrium after having guessed a support, which is what we set out to do. So the last thing I want to think about here is, what does it mean to play a mixed strategy? It turns out there are different interpretations. And now that you can really see kind of the mechanics of what's going on inside a mixed strategy, you're sort of better ready to understand some of these different interpretations. So the first and kind of most natural is kind of the one that is going on in the matching pennies example. And that is that you randomize to confuse your opponent. So in matching pennies, we each want opposite things. And the only way we can be in equilibrium with each other is if you have some kind of uncertainty about what I'm going to do. If you know for sure that I'm playing heads, you just know for sure what you're going to do, and it's something that I don't like. And so there's no pure strategy in this game. So the only way that we can be in equilibrium is if we're both a bit confused about each other. But that doesn't really describe what just happened in the the Battle of the Sexes example that we just played. Here, the other player and I kind of want to coordinate. The situation where we both end up in different places, where one of us goes to the football game and the other one of us goes to the ballet, is kind of an unhappy thing for both of us. What we both prefer is that we're both in the same place. And the only kind of strategic element of the game comes from the fact that we have different preferences about our most preferred activity. So in the mixed strategy equilibrium here, it's kind of an unhappy thing because, of course, when we play this 2/3, 1/3 equilibrium that we just looked at in Battle of the Sexes, where we have 2-1, 0-0, 1-2, if we're mixing, there's some possibility that we're actually going to end up in these uncoordinated outcomes that neither of us likes. That's just sort of an unhappy thing about the fact that we're playing a full support equilibrium. But and so it can't be that we're randomizing to deliberately confuse each other. Instead, we should really understand this randomization as reflecting uncertainty. So if I'm uncertain about the other person's action, then I best respond given that uncertainty, and I do that in a way that leaves you kind of uncertain in a particular way, we can also find ourselves in balance. That's really the way that I understand the stability of the equilibrium in Battle of the Sexes, that if we make each other uncertain in a precise way, we can find ourselves in balance, even though we would really like it better if we were just to end up in one of these pure equilibria. There are two other interpretations that I'll mention here just to be complete. We can also think of mixed strategies as a concise description of what would happen if really nobody randomizes, but we just play the game repeatedly. So you can think of a mixed strategy as the count of the pure strategies that would occur in the limit. And you can see how that might also describe what happens in the Battle of the Sexes game, where if we just sort of bouncing back and forth between the different strategies, weighting ourselves in that 2/3, 1/3 kind of way, we would be in equilibrium and sometimes we would miscoordinate. The last interpretation is that mixed strategies describe a population dynamics. So if it's the case that we have whole populations of player ones and whole populations of player twos, and we sample players from the population, each of them has a deterministic strategy, the mixed strategy can be an interpretation of those population proportions. So if it's the case that the one population has 2/3 Bs and 1/3 Fs, the other population has 1/3 Bs and 2/3 Fs, if we were sampling those populations would be in equilibrium relative to each other. So that's another story we can tell that explains what equilibrium might mean, what it means to be playing a mixed strategy, and to be in equilibrium there. And that concludes our discussion of how to compute mixed strategy equilibrium.